Now let me just say a thing about templates. Templates are not a beginner's approach to programming. I told you in the intro video that the method we're going to learn in this course is what I do when problems get hard, and that's true. So what templates are, the way we mean them in this course, is they're an expert's way of saying, gee, before I start on this function or before I start on this program, what do I know about the basic structure of it before I get to the details? So data-driven templates are saying, given that I know what type of data this function consumes, what do I know about the structure of this function? And the Big Bang World Program template is a way of saying, given that I know I'm using Big Bang, what do I know about the basic structure of this program before I start? And later on in the course, we'll see templates where we know, given that I know I'm using this basic kind of algorithm, what must be true about the structure of the program before I get to the details. Templates are an idea that you can use throughout your career no matter how sophisticated a programmer you get to be. When you get a hard problem and you don't quite know how to do it, you first say, well, what do I know about the basic structure of the program before I get to the details? That's an incredibly powerful idea, and it's not one that's just for beginners. In the last video, we started on the problem of designing the world program that causes the cat to march across the screen. And we did the first half of the world program design recipe. We did the domain analysis half. That produced this domain analysis for us, in which we identified constant information, changing information, and the required Big Bang options for this program. In this video, we're going to start on the second part of the How to Design Worlds recipe, the build the actual program part. And we're going to do steps 2.1, 2.2, and 2.3 in this video. So let's get the starter file. And what I'm going to do now is I'm going to go to the How to Design Worlds recipe page. And I'm going to scoot down here to the bottom. And I'm going to take this template of a world program. And I'm just going to copy this whole template right here and bring it over into my program that I'm working on. Now templates do something else important, or what I should really say is that the way the recipe is structured does something else important, which is templates break the process of design down into steps of the process, not just pieces of the solution. So this function and that function are two pieces of the solution. But what the template is it's a step in the process, because when you have the final function, the template is kind of buried in the middle of it somewhere. That's really important. That's what happens when you design a method, is you can design it so that you both get pieces of the solution and steps of the process. And so you get a kind of cross-cutting decomposition that helps break the overall work down into smaller and more manageable pieces. So don't let anyone tell you that templates are just for beginners. Nothing could be further from the truth. What is true is that as you get to be a better programmer, you won't template very simple functions, or you'll kind of template them in your head or something. But the idea of templates, the idea of getting the basic structure of a piece of code before you get to the details, you'll always have that idea, and you'll always use it when the problem gets too hard to just immediately write down the solution. So here we go. We need a better title than this. A cat that walks from left to right across the screen. Right? The first line of a program should give us a short summary of the program. Now we're going to do the constants. And the constants are going to come directly from the analysis phase of the program. This analysis here. So for example, one of the constants we identified was that the width of the screen didn't change. So here I have to just guess a number. I'm going to guess a number like 600. In the rest of the program, we're never going to use the number 600. We're always going to use the constant name width. So if it turns out that this is the wrong number, it'll be real easy to change. We'll only have to change it in one place. Here we go is the height, and I'll say 400. Another constant we identified is the y-coordinate of the cat. The y-coordinate of the cat never changes. So that's the center y. And now here you might be tempted to put 200. But what I'm going to do is follow the rule that every time I need to refer to the height, I'm going to use the height constant. So what I'm going to do here is put height over 2. Now if I change height, center Y will also change. And let's see, for the empty scene, the background of the scene, there's a primitive called empty scene, and we'll make it width by height. And that'll give us a sort of blank background. If you wanted to make a background, that was a nice midnight blue or something, you could, for example, instead make this overlay rectangle width height mid solid blue, and that would give you a blue background. I'll just stick with the simpler background for now. And the last constant we identified was the cat image itself. Okay? And for that, we're just going to use this image here, which the starter file gave us. I'll go up there and copy it, and then I'll come down here and paste it. And there's the cat image. And now would be a good time to run. In fact, I should have run after each of these definitions. And I don't get any errors, so I know that my constants are well formed. Now let me reinforce a point I made before about using the constants and always referring to the constants. Notice that this code that I have here lines up really well with the analysis we did. The fact that I can look at the analysis and look at the code and understand where everything in the analysis showed up in the code is a thing called traceability. Both of those are important for the same reason. And that is, this is an important intuition. The way to think about it is there's only two kinds of programs in the world. There's programs that change and programs that nobody uses. Put it another way, any program that anybody uses is always changing. People always want it to do more and better things. And so what we're doing here is we're designing this program to make it easy to change. Using constant names makes it easy to change. Having a clear traceability between the code and the analysis, we'll see later that makes it easy to change. Okay, let's keep going. Now I've got the constants. The next step is to do a data definition that corresponds to the changing state of the program. The changing state of the program for my domain analysis is the cat's x-coordinate. So that's simple atomic data. That's going to be something like a number. The world program template has the beginning of a data definition here. It has WS for world state, but it says to give WS a better name. And sure enough, I will, because WS isn't a very good name. I'll just call it cat. And I'll say cat is, let's say, number. And let's see, the interpretation is this is the x position of the cat in screen coordinates. And now I need some examples. And let's see, one good example is 0. And another example is, well, let's see, the middle of the screen is width over 2. So that's kind of in the middle. And that's kind of on the left edge. And let's do this one. And this is on the right edge. So we'll run just to make sure everything's well formed, and it is. Now we need a template, define fun for cat. And this is just an atomic non-distinct case, so ... C will fill in the template rules used of atomic non-distinct and number. And it's also good to comment out the template, and now we're good to go. So there we go. There's our data definition for cat, for the changing world state of the program. Now we're going to proceed to our main function. Now we decided not to use the name WS for the changing state of this program. We decided to use the name cat. So what I'm going to do here is I'm going to say Command F or Control F on Windows. I'm going to take every occurrence of WS and I'm going to replace it with cat. Let's see, we'll replace that one and that one. And I won't do that one because it's a parameter name and I don't want to mess up the case. I'll come back and do that one. But I'll do all of these. Oops, I didn't mean to do that one. I'll come back and fix it. I'm not going to do that one. And now what's left is these ones that are parameter names, and these I'll just change to C. And there's that one there that I messed up. And I'll just run now to make sure things are still well formed. So now here what I've got from the template is a main function that has lots of big bang options in it. Okay? I'm not going to use all these options. I'm only going to use onTick and toDraw. That's what my analysis told me. So I'm just going to go ahead and delete all of this. And I might decide that I don't like the name talk for the onTick function for this program. So let's see, I could change the name talk. Oops, I've got a parenthesis problem here. I'm going to change talk. I clicked on check syntax. Now I'll click on talk. I'll say rename talk. I'm going to call it advance cat. And I'll have to fix some of my spacing here. Now what's going on here off to the right is that the template for the world program in its main function is reminding us of the signature of each of the handlers. And the other thing the template for the world program did is for these two handlers, look at what we've got here. For each of these two handlers, we've got its signature, its purpose, but that's not filled in, and a stub which isn't filled in. Let me just fill this in now. It's produced the next cat by advancing it 1 pixel to right. And that means that a good stub is just 0, because cat is number. And this just says render the cat image at appropriate place on MTS. These two things here, the combination of signature, purpose, and stub with those exclamation marks are what we call a wish list entry. What we're doing here is we're saying, hey, up here when I wrote main, I assumed that this function advance cat was going to exist. And what I'm doing here is I'm writing a reminder to myself of what it is I want that function advance cat to do. I want it to have this signature, this purpose, and by the way, there's a stub. And this is a reminder of what I want the render function to do. I want it to have this signature, this purpose, and by the way, there's a stub. Now, once my program is set up like this, notice two interesting things about it. One is it turns out I can actually run it, and I could even say main of 0 and run it. Nothing happens, of course, because my tick function doesn't do anything, and my render function only returns the background scene no matter what. But it does run, and the reason it runs is I have these stubs for the two big bang handlers. I have a stub for advance cat and a stub for render. The other thing I can do now is I can search for bang, 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 and I can see every place in my program that's incomplete. By marking each of the wish list entries with some well-known marker that says, hey, this isn't done, I now know what I have to finish. So now what I've got is I've got the overall structure of this program set up. I've got the constants. I've got the data definition for the changing world state. I've got a main function that calls Big Bang with two options, onTick and toDraw. And I've got wishlist entries for advance cat and render, which are the handler functions for those two Big Bang options. And now I know what I need to do in order to finish this program. I have to design the advance cat function, or I have to finish the design of the advance cat function, and I have to finish the design of the render function. And then I should be done. That's what we'll do in the next video.